Good. That is cleared out. All right. So we are here. That is not the screen you want to see. You want to see that screen. Boom. All right. Today is not 4/16. It is 4/16. I am amazed.
Stream is currently looking at some frozen picture.
Time is moving forward. The stream. See, now you get to see it live, where just stuff doesn't work. What do you see? You see nothing?
The camera was working, so I think it's just the source.
Man. Screen capture. Go. Beautiful. You. Transform. Fit to screen. Do we... See, now my stream shows just blackness. Do you see? Okay.
Yeah.
All right. I think we're good there. Go there.
Your camera got deleted.
OBS.
Or they got deleted or put like in the background.
Yeah, it's always behind. All right. Do I have audio? Yes, I do. Okay. So, if the camera will look down, man, this Discord bot is so useful. You almost missed the stream. I don't think we did anything with the Discord bot. Did you do something with the Discord bot, Twitch? Did you actively make a meaningful contribution to our community you have gained so much from? That would be so impressive. In any case, I think we're done with technical difficulties. Today is April 16th, 2024. We're on week 14 of CSE598. We are talking about kernel exploitation. We are still going on kernel exploitation. It's been a long road of kernel exploitation. Memes. I don't know if I have repeats here. I kind of lost track of time. First one here, free list randomization protection. Spray the object. Okay, right? Easy, low-hanging fruit. I'll take it. All right. Take what we can get. Twitch says they didn't make any meaningful contributions to pwn.college. One day. All right. That should be like its own belt. In fact, it is. It is like its own icon or emoji that you can earn by contributing. Other memes. Defeating the hardened free list. We read the pointer values, and somehow we panic by reading, which you shouldn't panic by reading. So I don't know what you got going on there. But it is part of defeating the hardened free list values is reading the hardened pointers, as I think we saw in office hours.
Yes.
Okay, cool. I don't remember exactly what I did last week, but I think that was part of it. And then I think this one is a repeat. But, you know, I empathize. You panic, I panic, we all panic. I just do it on camera for your entertainment. Right here. I like this one. All right, that's a meaningful contribution. Doesn't get you an emoji. Modules, I know how to solve drops, and you feel awesome. Completely new module material drops, and I don't know if they're in a bathtub, but I'm going to assume they're crying in a bathtub. All right. It is kind of funny how you can feel so empowered going through this material, and then you run into something like brand new, and it's very hard to relate to it. And so there's this like the vicious cycle, right? But hopefully you end up on the other side of the curve and everything makes sense and you go back to feeling empowered. This module as a whole is this picture. I don't like it, but it's a fact, right? The entire module in kernel exploitation in general relies on kind of knowing these like golden nuggets, like mod probe path, or what we're going to talk a little bit about today, which is message and pipe buffer. And if you don't know how these like specific mechanisms work in the kernel, you'll kind of be left struggling without having a direction to pursue. What do we got for our last meme here? Writing the code to solve the challenge. Let's not do that. Instead, let's wait for class to see the demo of the same code and then only write it after Robert has demoed it. This is not a mean meme, but it is a meme that I feel. All right, you guys have been hitting some nerves lately, and that is one that I personally feel because I hate demoing solutions live on stream. And so I'm not going to do that today. Thank you for reminding me. Course schedule, we're still plugging along here in Kernel Exploitation that runs forever. At the end of this week, hopefully we will throw the multi-host exploitation, which we started rambling about like 3 weeks ago. That will actually exist. And then we will march forward from there to the end of the semester. It shouldn't be anything crazy daunting. Logistical things. Somebody brought up the checkpoint date was set to, I think, today. I moved it to the end of the 3-week period here with the kernel module. So if you did not finish the first half by now, you aren't going to get penalized. Secondly, people brought up course/instructor reviews are getting deployed. If you have them, you can fill them out. Feedback is always a good thing. So my plans for today is actually a little bit different than what we've done historically in this class. Usually I try and jump into a terminal, start poking at things, looking at things and ranting. Instead, we are going to kind of do a live pre-recorded lecture that is not pre-recorded of the slides that doesn't have a pre-recorded lecture. The reason for that is I don't like anything that I would say in the pre-recorded lecture. I've looked at those slides. I've kind of marched my way through them. I'm not content with it. And so instead of just kind of hanging around, twiddling my thumbs and being annoyed at it, we're just going to run through it live here and see what comes out the other side. Because conceptually, you need to have this knowledge. And I think it's a little bit more interesting, or at least a bit of a trial, to try something different here. So we're going to run through the unrecorded slide deck that has been up there all week. There will be no full solves today. Yes, live pre-recorded lecture, which makes it a live recorded lecture. All right. With that said, anyone have any particular questions or something they're stuck on? Conceptually, if you have seen the office hours from last week Friday, you should be able to solve everything up until, I believe, 5? 5. So if you are not up to level 5, what I say is probably not going to help you. But when you get to level 6, 7, and 8, these things will. All right. Oh, no.
The next module is still planned to be released on Friday?
Question. The next module is still planned to be released on Friday. The answer is yes, it is planned to be released on Friday. I will emphasize the word planned. If things, for whatever reason, do not pan out and you feel I'm being absolutely unreasonable, just like DM me, let me know. We'll sort it out. All right. Does someone have like some monster final project that is looming?
Calbot FS.
Are you tackling Calbot FS?
After I finish level 8, yeah.
That's awesome. I don't know if it I should look. Did Justin solve all of them?
All of them. He's the only one still.
Okay, yeah, then that's fair game. Justin is not mortal, so like he doesn't count. Kyle doesn't count. Justin doesn't count. You'll get made up class points if you solve it first. So have at it.
Awesome.
Right. Plus we'll make a trophy and throw it on the screen or whatever with your face on it if you want. Be like #1, right? It'll be amazing.
First one to solve except Justin.
Yeah, the first person that it doesn't like have their entire graduate study be kernel exploitation.
Yeah.
That would be awesome. Like I want to try and take a stab at them myself, but I don't think that's quite fair to compete. But yeah, it probably would be a level playing field. Okay.
Saying it's really hard.
So. I don't trust anything those guys say. I have learned that. I have learned to trust but verify. It's like there's some nugget of truth in there, but you know what is more correct than the mouth of Justin or the words of Kyle? GDB. All right? GDB will never let you down. GDB will never misstate something incidentally. All right? Go to the truth. So, this is our third slide deck here entitled Kernel Exploitation, Exploiting the Kernel. I assume we've seen the first 2 lectures. Can I make that assumption? Yeah? All right. So, in general, when we're talking about kernel heap, we've seen that these other basic type of vulnerabilities exist, right? The earlier levels, like levels 1 through 5, we experience an out-of-bounds access, like buffer overflow or reading out of bounds. In, I guess, levels 1 and 2 of this module. 3, 4, and 5, we no longer have this out-of-bounds access, but instead we're playing around with use after free. So we can free something and then we can start messing around with the bytes that exist in that slot. All right. Now, why would we care about this use after free? Well, it's the same type of thing we care about with the userland heap, right? We can leak metadata. In the case of the kernel heap, we can access the free list. We can corrupt metadata, so we can overwrite the free list. That gives us the ability to create primitives like arbitrary reads and arbitrary writes, which hopefully at this point we have some idea of how that works. We can also leverage these arbitrary primitives to create other primitives that we may need, such as overlapping allocations. I believe that overlapping allocations is level 3, if I remember right. And 3 is interesting because it has a function pointer in the kernel object that's being allocated in the cache there, right? And so that gives us kind of an easy target to gain control flow, right? Or to turn our arbitrary read, arbitrary write into execution. And we also saw in, is it 3, 4? The kernel can randomly place objects, right? The free list can be randomized. So when a new slab is created, you have no guarantee about the order. And in fact, you have no guarantee about kind of the state of a slab in general. Levels 1 through 5 all use a dedicated cache. Did you guys notice that? By chance? We're being all super nice. Dedicated cache. There was nothing crazy going on. Even like level 8 is actually quite nice, as Kyle repeatedly reminds me. For a slightly different reason. When we looked at level 1, so let that fire up over there. When we look at level 1, the cache that was being created at kheap init, that's ioctl, at init, was doing kmem cache create. It was creating, no, that's not it. Yeah, that is it. Kmem cache create, where it's creating a cache for objects of size hex 1b8. And so that is a dedicated cache, which we saw over here inside of the VM. So I'm a believer. Yeah, the VM does in fact start. And when we looked at slab info, we saw that there was this dedicated cache for kheap objects. And what that means is there will never be some other object allocated on this cache. There is nothing else going on in the kernel that's going to fill up a slot from this cache. Because remember, yes?
Like there's no extra noise basically in the environment.
The comment was, so there's no extra noise in the environment. And yes, that is exactly what I'm saying. Right? There's nothing else running on the kernel that is going to allocate against this cache. And so that is a super convenient thing for us to kind of begin our discussion or exploration about how the cache works. Because the only thing that's allocating anything is us, and the only thing that's freeing anything is us. And we may have to do it via this ioctl interface. We may have to do it with this like weird request struct thing that we have to build. And that's kind of a means to an end, right? But we know that there's only one type of object in this cache, and we know that we're the only ones that are interacting with this cache. And so that lets us know several things that we don't necessarily know in a general sense. Somebody says, hey, please talk about level 6. I could talk about level 6. Don't know that I'm going to. So that was something that was useful, right? So we didn't really encounter this scenario. In level 6, not because you said it, but it happens to be the first level, where it says, hey, we're working on the real Linux kernel heap. So what does that imply? And we're working on the real Linux kernel heap. Well, if we fire up the VM and take a look at that same stuff, maybe. What we'll see is that it does not call kmem cache create. In fact, we don't see anything particularly crazy going on over there in init module. And inside the ioctl, we get this kmalloc trace in Binjo. Let's see if IDA shows something else. So I'd rather not go down chasing what is kmalloc trace. Did Adam go down the rabbit hole? I'll just keep opening up different decompilers until I see something I like. Okay, so I'll trust that Adam did go down that rabbit hole, and I will just tell you that it is calling kmalloc. And we can, for those that are inquisitive, we can go to our source. We can find 679. What was this thing called? Kmalloc trace. Cool. It's defined. That's not where I want. I want slab common. Slab.h is dangerous. You want slub.h or slab common. And this is creating an allocation I'm claiming. It has a size argument, so that's a good thing to know. And if we go back to the search, we'll see that it is referenced in slab common. And where did I go? 1106 and covered up. That's exported. That doesn't help me. It's called in kmalloc, though, I promise you. Is it going to be in the dangerous slab? The slab file is danger. Okay, there it is. So it is inside the danger file that I said not to look at. Kmalloc itself calls kmalloc trace as an implementation. And if we think about how these caches work, just like in general, it makes sense. If I want to have some type of general malloc function, and these caches are size specific, then what would like a basic implementation of kmalloc be? Like, what do you think you would do? I would say, hey, what size do you need? Do I have a cache that does this? If I do, let's use that cache to return the object. And that's exactly what we see happens right here. When the kmalloc function is called, it just gets a size and then it flags. And what is it doing? It's looking for a cache of a reasonable size for what is requested. It's then going to call this kmalloc trace on the cache that meets the requirements that are needed. So we can think of that as just calling kmalloc. Now, what do we know about kmalloc? Do we know anything about kmalloc? I don't know if we know anything about kmalloc. I think I got kmalloc hiding down here. Ooh, no. So I did talk about kmalloc. You know, not you guys. Okay. So kmalloc is the general allocation, right? What caches does kmalloc use? It uses, yes, I know, it's a surprise. This was a link for Tuesday recitation. This is not recitation. Okay, thank you for taking care of whatever logistics are going on there. Yes, when kmalloc is called, it is going to use one of the aptly named kmalloc caches. And they are named kmalloc followed by the size of the slots that are offered there. Now, one of the things that Adam touched on is the difference between kmalloc and kmalloc, where is it? Kmalloc CG? Anyone happen to recall what kmalloc CG does? No? Oh, I'm not in the VM, that's why. I don't see it there. So if kmalloc is called normally with a kernel object, then it will be in these nice kmalloc spots. But if kmalloc is expected to use user or hold user data, right, something that the user can influence, then there is a separate cache that will be used. And that is this kmalloc CG. And so what we're doing, you'll notice the sizes are the same. We have 256 up there, we have 256 down here, right? They essentially mirror each other. It's just untrusted user data will be chilling up here in the CG cache. And then everything that stays in the kernel hangs out and down in the normal kmalloc. The other two, they exist as well, but we're not going to delve into those. The way that something gets allocated in this CG is by specifying, it's in the slides, what is it? GF. Yeah, that one. GFP Linux account? Kernel account. I knew it was GFP, I knew account, I didn't know the middle word. GFP kernel account. If that flag is specified, then kmalloc will use the CG cache instead of the generic caches down here. Now, what is a side effect of not having a dedicated cache, which is what we had in levels 1 through 5?
Other stuff can be in there.
Other stuff can be in there. That is a problem?
It's intended, but it's a problem for us.
Is it helpful?
Good.
It's good. So we got it's good, and it's intended, and it happens. Can it be bad?
We're trying to
It kind of changes the rules of the game. All of the above are true, right? So initially, we were like, well, we're the only ones that put objects in the cache. That's great, right? We can know the state of things. But now that we're going to use these general caches with kmalloc, that means there could be objects in any one of these slots. There could be tree stuff in any one of these slots. And in general, our kind of goal is to allocate some kind of target object and then get our attacker-controlled object right next to it. Well, that becomes a bit harder when you have like this unknown state of the slab. Right? So how can you deal with that? Oh, we can just fill it. We can just allocate a bunch of things until we know we're on a new slab. There's one thing that could be done. And once we've done that fill and we're on the new slab, we can recreate something that is similar or more favorable to our scenario, where we now control a larger number of objects on the slab. So then when, there isn't a slide with that, but then when the victim object gets allocated, we have a high chance of it being right next to our controlled slot. Somebody asking CG, C group. Yes, C group is a word. It is relevant to the letter CG. So we said it was good and it was bad, right? Because kmalloc returns objects from the general use kmalloc caches. And it can hold many different types of objects. So the problem is there's a bunch of different types of objects, but we could use that to our advantage, right? Because what we saw in levels 1 through 5 is how did we create objects? Well, we just used this magic ioctl thing. The kernel did it for us. It was nice. It called kmem cache. But the kernel creates objects all of the time doing everything. Like you create a pipe just in your userland code. Where does the memory for that pipe come from? Right? It has to get allocated somewhere, right? When the kernel needs to do anything, it needs to like allocate some memory. And how do we interact with the kernel to cause the kernel to do anything? Syscalls. So In levels 1 through 5, we were kind of restricted to this idea of what actions can we do. Well, because we're only interacting with this nice little K-heap cache, the only things we can do is we can open, we can ioctl, we can close. And everything goes in this nice little package kernel module because that's the only thing that touches the K-heap, right? But now that we're in the general cache, every object is a valid interaction. Anything that we could do, any syscall that we could perform, could interact with a cache, and probably does, to be completely fair. And so now our kind of strategy and tactics that we can use has drastically expanded to literally every single syscall that we can call from userland. And each of those syscalls, if we look at how they are implemented in the kernel source, will either be creating or freeing allocations on these caches. Now, it wouldn't be quite fair to just say, okay, every syscall is fair game, and there's 200 and some odd syscalls, so go read all the source and figure it out. It turns out that not all kernel objects are created equal. There are some that are quite favorable and frequently used in exploitation. Twitch is jumping ahead of the game. Something about message objects. We're almost there. So why are some objects more desirable than others? Well, we said that the cache holds a fixed size. So one of the things that we may want is an object. Well, I can control the size of it. If I can control the size of the allocation, that controls what cache I'm interacting with. So if there is an object or a syscall that I can perform that allows me to determine the size of the object being allocated, that is very handy. We saw in the the pre-recorded video that came prior to this one, the second one, we talked about the protected, what was the name? You know these.
I didn't.
Oh, you don't. I want to get the word right. So I'm going to misquote this one. Protected copy, hardened user copy. So if the hardened user copy is enabled, then copy to user and copy from user are bounds checked. And that prevents us from getting a kind of out of bounds read or an out of bounds write that we had in earlier levels. So something else that may be desirable in an object that we want to allocate, free, somehow get onto our slab is an object that circumvents copy to user or copy from user, that doesn't follow the rules of this bounds check. And then lastly, is kind of a callback to levels, 1, 2, maybe 3? The K-heap object that we started off with, it had a function pointer. So in the first couple levels, what was a very nice thing to overwrite? The function pointer, because that allows us to then direct control flow from the heap. So if there were some type of kernel object that we could allocate that had a function pointer, that is essentially creating the scenario that we had in like level 1. Right? Except instead of everything being packaged nicely into this K-heap object that has all of these properties, we have to find the objects that have the properties we want, place them on the slab, and choose them wisely. So there's 2 objects in particular that are worth mentioning that are stressed in this module and the attached reading material. The first one is something called message. The second one is something called pipe buffer. Anyone familiar with message? What it is? Is it message overview? What's that?
I think Adam mentioned it yesterday.
Adam mentioned it. Adam can't steal all my thunder, okay? That's not fair. I'm not on the dojo. Okay. So man 7 is like a high level, what does this system of things do, right? You're familiar with pipes, right? We use that for IPC, communicating between processes. There is another mechanism. You've heard of signals. It's another IPC, communicating between processes. Turns out there is a whole other IPC mechanism known as messaging, with POSIX message queues. And this is used, as it kind of implies, for passing messages from one process to another. Typically, there's 3 syscalls that are going to be used. Message get, which is how you obtain a queue. Message send, which is how you send a message down the queue. And then message receive, which is how I grab a message off of the queue. So conceptually, it's not too crazy. But why are we interested in message? Well, message is a little bit weird. If this link works. Nice. So this is the head of a message. So when we call message send, the kernel allocates a message object. And one message object consists of this header followed by the bytes of the message itself. And if we were to go back and look at message send, MSG SND, message send, you'll see we specify a queue, we specify a pointer to the message buffer, we specify a message size, and then there's some flags. The key part here is we can specify this size. And then there's a header. What property do we have by messing around with message meshing so far?
Ability to change size of there.
Right, we have the ability to change the size of what is being allocated. And so this allows us to allocate anything. This header is hex 30 bytes. So hex 30 bytes plus whatever the size of our message is. There is some limit as far as how large the message can be before it gets like broken up into segments and something else. It is 1 page. So that is something useful because now I could specifically target a cache that I'm interested in. This is in the VM. Let's see if wild demo code that I don't remember if it works or not works. Cool. So this is my message demo here. I am saying that I have a target cache. My target cache that I want to interact with is the 128 byte cache. I just kind of picked that because it's a good looking cache. I wrote this nice little replacement that could have just been getchar, but I like easy block. All right, I feel like it has more flavor to it. My main function is pretty boring. What are we going to do? We are going to set our message size to be whatever my target cache size is, minus hex 30. Why hex 30? Because that's the size of the message header. The size of this buff doesn't matter. I'm filling my buff with 1, because if you read the man pages, the first byte, or the first int, not the first byte, but the first 8 bytes, 4 bytes? I don't know. The beginning of the message is an int, and it needs to be a non-zero number. So I'm just writing 1 a whole bunch of times because I actually don't care about the message contents. I'm just satisfying this non-zero constraint. I then have a giant list of message queue IDs, just an array. You can take 100 of them. So it's going to block before we create all these messages. I'm then going to loop 20 times. Inside my tight loop, I'm going to call message get. Message get creates the message queue. In order for me to send a message, there must be a queue for me to put the message in. So I am creating 20 different queues, and I am throwing in a message in each one of those queues. It wouldn't surprise me at all if the act of creating the queue also does an allocation of some size. I don't know. I don't care. What I do care about is the cache of 128 bytes. We're then going to break and say, hey, we made all these messages, so we can take a look. We then are going to loop through here another 20 times, and we're going to receive those messages that are full of ones right back out the other end. Everyone on board with what the code does? All right. Hopefully, this is visible. So, what level am I in? Level 6? I don't want to be in level 6. Level 6 does not play nice. We'll go to level 1. Like, you can get around the KASLR, like by setting the text segment of the ELF, manually specifying it when you set symbols. There's a GDB command that does it. I don't have it memorized right now off the top of my head. So instead, we'll just go to a challenge that doesn't have KASLR. Because then when you use something like libslub, it will behave. Okay, so we will... Oh no! That is never a good thing. 142, you don't like a colon? What do you not like? It's because you don't need to be there. All right. Warnings are just suggestions. We are off to the races. All right. So we'll connect in the left-hand side. Right-hand side is covered up by my head. So we will throw that down here in the bottom right. Fancy demo? Yeah, you know, only the best for you, Twitch. We're going to source libslub, libslub.py. The reason I want to use libslub, we could cat proc/slab info, right? You've seen that happen plenty of times. What I have noticed personally is it shows an upper bound, but it doesn't necessarily show a lower bound. I don't know if that's just a me thing, but like I've allocated stuff and then freed stuff, and the slab info hasn't gone down. But I have seen that reflected in libslub. The nice thing about libslub is it has this SB list. Hey, it's showing us that same data. I can then filter it by a pattern. In this case, we're interested in the 128. And so this is what we're working with right now. Okay. I will tell you right now, message. Does it contain user data?
Yes.
Yes. So which one of these caches?
Second.
CG, yes.
Yes, the CG. We should be seeing a change from running this code on this in-use number on CG 128. Now let's see if that's what actually occurs. Sometimes it doesn't. Okay, above my head, I'm going to compile it and ignore all warnings. We run this. Okay, before creating messages, we have a number. It's still 37. So far, so good. After creating messages, we were at 37. Please be somewhere around 57. Oh, what do you know? It's a good day when the demo gods bless you. It is exactly 57. Now, it could have been some number that wasn't 57, right? As long as it like was up, was larger, I would have accepted that and been like, the kernel is doing something, because this is a general purpose cache.
Things could have been removed. Things could have been added.
Yes, so I think things could have been allocated, things could have been freed, completely unrelated to anything that I was doing, right? That just happens to be the case here. So if this was 55, totally fine number. If this was 63, totally fine number, right? Because we do not have complete control over all of the allocations and frees that are going against this general purpose cache. Now, I said that these later challenges are also kind of nice, and that is because this VM, part of the reason the VM is slow is because the VM has a single core. Right? If the VM had more cores, you know what the likelihood of other random activity going on against your cache would be? higher because you have more cores going on, so you have more activity going on that are interacting with these caches. So we saw that. Let's see if we can bring it back down. Let's see if we can finish the demo strong. We're going to continue. We are after freeing. Now you laugh, okay? You try and make a demo that is as perfect as this. The number went up by 20, and then it went down by 20. All right? So it's way harder than you think. So we saw that I was able to create these allocations in the kernel by doing this setup right here. I created a queue. Now, does creating the queue, is that what did the allocation? No, it was the act of sending the message at the size that I specified. A question you may ask, well, Robert, why don't you make one queue and send 20 messages in that queue? That could work, right? Because it is the act of sending messages that is the allocation. However, what you'll find, if you read the man pages, is you can block on this. It is a queue. It is not an infinitely large queue. And that goes for sending and receiving. So
the limit is 4 pages.
This individual happens to know the exact limit is 4 pages. So you could run right up against that 4-page limit per queue, or you could just say, I don't need to know that magic nugget, and I'm going to make a queue for everything that I send. Right? And so this is how I was creating those allocations, and then every time that I perform a message receive, I was freeing one of those slots or freeing one of those objects to create a slot. Now you'll notice that this isn't specific to K-heap. I just targeted the 128 general purpose cache. On level 6, what cache was it using?
200 in hex.
Every number, man, ingrained. All right, you were just in the zone. But yeah, we didn't change it, so it's not a surprise. Levels 1 through 5 was hex 200. So level 6 is also hex 200. So you can't use exactly this, but now we have an approximation where we could use this type of logic to interact with the cache that is responsible for hex 200 size objects. Twitch says that's the first demo that you've seen go perfect. That is not true at all. I think I have I don't know, I'd say probably like 80% success rate on demos.
Well, it's went done flawlessly from step 1 to step finished.
You think it's the only flawless?
I agree.
There's
Really?
There's usually some like mucking around in GDB that needs to happen, which is educational.
But you know, the mucking around in GDB is like half the fun, right?
That's true.
We should have mucked around in GDB on this. In fact, prior to class, somebody was asking me, well, how are you going to incorporate GDB into this? Yeah, and I said, I'm not. Instead, we're going to just keep talking about slides.
Do you know what kind of memory gets allocated when you create a message queue?
I don't. Like,
Just the queue, though.
yeah, just the queues, and that was in message get, right?
20, OX20, like 32, came off 32. Right.
Like, don't be talking about secret numbers, number man.
It's important.
Oh.
It's important stuff.
Oh no, that's fine. It's fine that we all learn together, but like that there's an online component to this class. We have the power of technology in the entire Linux kernel source code in front of us.
Talk about the size of a message queue.
That I am perfectly fine spending the remainder of my time, the next 8 minutes, answering this
I guess
question.
that wouldn't. Well, Sean just said 32 bytes, and I guess that wouldn't mess with an exploit because the minimum message size is 48, right? That's the message header.
I mean, that's a different object.
Right. No, I'm saying, but I'm just asking if it was going to interfere with an exploit.
Okay.
Depending on when you create the queues. Like if you create the queue for each message, or if you
Usually do exploitation, we just create
at
a
the start. Yeah, that's what I was thinking.
So I am proposing that it is quite large.
How big the queues are.
I am completely and 100% arbitrarily guessing that it is this struct right here, which does not appear to be insanely large. We got one pointer, so that's 8 bytes. This is 16 bytes. That's hex 20, hex 28 would be my guess. Now, I didn't chase the source code to find this exact struct being in use, but this seems like a reasonable. Am I right or wrong? Magic Number Man, you said hex 20?
No, I regret it.
You regret? It turns out going to the source, finding absolute truth, revealed greater knowledge.
KMalloc 64.
It's what?
Queue. KMalloc 64. No, like that's what I'm saying. Where the queue would go. The name of the queue is I think just message underscore queue, like MSG underscore queue, right, Sean?
Message underscore queue.
Message underscore Q, IPC message.
Pretty big.
That is pretty big. That's definitely not hex 20.
Sorry.
So, yeah, you could mess with your exploit if you're
targeting a small
targeting 64 byte.
Can we see?
Depending on when you
That's where it's defined. Where is it used? I want to see what. Ideally, what we want to see is where is the.
Well, I assume it's allocated when you do the message get IPC create thing, like when you create.
Yeah, and so that's what I wanted to see. Like the thing to really find is message get.
Yeah.
Right. Well, where is message get inside the kernel?
Yeah.
Right. But when I initially, that was the.
Syscalls sometimes.
Yeah. That was when I did this and it said, hey, we don't know that word. And then I just let's just find out. I don't know. Here's something that looks right.
It's gonna be like sys underscore message get or something ridiculous.
Yeah,
it's not worth it.
Okay. But we could.
Yeah.
We could. All right. And the takeaway there is not that I found the right thing, but that we didn't trust an arbitrary number that came out of thin air. All right. We can spend the time and look at the source to find the answer.
I have to correct it so answer is 100.
What is it?
100 in hex.
100 hex. That's actually quite large. But this is still just an arbitrary number, right? Until you post the link to the source in Twitch, this is a magic number that I don't trust. So you either post the source or it's all smoke and mirrors. Okay, so we derailed a little bit here, but it was a fun derail. So we were talking about message. So message is cool because we can influence the size. You know what else is cool about message? It has this size value. This is the header. So how does the message receive know how many bytes to read for what is the user component of the message? Oh, it's this value right here. In a use after free scenario, that might be something worth mucking about with. So the mlist is a pointer to the next message in the queue. It's this linked list, right? And then MTS determines the size of the current list. So this has several valuable things from an exploitation perspective. This potentially gives us an out of bounds access, and then pointers are always fun to mess about with, as you've probably seen in prior modules. If you can overwrite a pointer, you can make good things happen. Yes, so we can control len as we saw, and yes, this is important. Inside of message received, definitely check out the source here. You can specify an argument with the flag called message copy. Message copy will change the behavior of message receive. So by default, when I receive from the queue here, what was happening? I was freeing that allocation. Right? That makes sense. Pulled it from the queue. I'm done with it. The kernel can free it. Who cares? It's now user land's problem. If instead we specify this message copy, this will peak. And if you look at the source code here, this doesn't free the allocation. And it also uses memcopy. Just a little bit interesting. May have some use. The last struct that we're going to kind of touch on here is the pipe buffer. Pipe buffer. Again, IPC. IPC is like all over the place here. Right? The pipe buffer itself is not particularly interesting, right? What do we have here? We have some page pointer, some offset thing. I don't know. But what is interesting is this pipe buff operations. One of the things that we do not do currently on pwn.college, but I believe we absolutely should, if I had infinite time, we would, is we would spend more time messing about with vtables. Like see, we would reverse some C++ code and look at vtables here. But while one of the pointers inside pipe buff points to this pipe buff operations thing, pipe buff operations is just a series of function pointers. And the comments here kind of give you an idea of when these functions are called. So what do you think we can do with this? If I get a pipe buffer somewhere on a slab and I overwrite one of these pointers, remember how we had bin format? What were we overwriting? We were overwriting a string to cause, what was the name of the mod probe path? Right? We overwrote that string mod probe path, and then we triggered that functionality inside the kernel. Right? It wasn't like a one-off thing. We changed how some functionality was going to work, and then we triggered it. We have a similar idea here with this pipe buff operations guy. It's a series of function pointers. These function pointers are triggered based upon certain actions from user land, and the kernel will call into them. So if we were to somehow overwrite what the kernel thinks is a pipe buff operation struct, and we could overwrite these function pointers, we could trigger the conditions that would cause the kernel to reference these pointers that we control. That is a fantastic way to gain control flow. And in fact, that's one of the reasons why this last slide deck is what it is. Because that is kind of the core of kernel exploitation. Is you think about what you can do with the heap, you think about these different objects, you have all of these different kind of tools at your disposal. And how you apply them or kind of mix them up is up to you. One of the things that has been on this module from day one is a series of linked recommended reading. And the recommended reading uses these objects. And it goes into great detail about how these objects and these pointers can be used to exploit the kernel. The whole write-up is there. It doesn't make sense for me to regenerate that entire write-up in a series of slides that you may or may not even look at. So instead, read the write-up. Hopefully this gives you some idea of why they're using message. Why are they using pipe buff, right? How do these pointers relate? Right? The purpose of this slide deck isn't to show you how to do it, but to give you the knowledge so that you can look at those write-ups and apply that knowledge. Right? And this is one of the things that is in the write-ups. Is like, hey, they create an out-of-bounds write from some of those objects that were described earlier to overwrite a pointer, which then creates a use after free. And then once they have a use after free, they can pivot that even further into something more powerful. We already talked about bin format and mod probe path. So I don't feel the need to reiterate that. If you are first learning about mod probe path from this slide deck, check out the stream prior. Does anyone have any questions about the slides, content, things that were discussed here today? We're all good. It's unusually muggy in here today, so I'm sure we all want to get out of here. While I'm still on stream, because I just want to see, can I get a thumbs up, thumbs down for slides over demos? Thumbs up for slides. Thumbs down for demos. Okay. Mixed. Very mixed. Okay. I was just curious. Because it's not something I normally do. I got nothing else here from Twitch. Somebody says, is IPC realistically used for anything other than kernel exploitation? Yeah, sometimes they use it to like communicate between processes. I don't know, man. That's what I heard. With that, I'll leave you all. This should be everything you need combined with the write-ups to do 6, 7, and 8. It is due in a week. And yeah, goodbye and good luck.